In this lecture, we are going to talk about inverse functions and their derivatives. In order to have an inverse function, a function has to be one-to-one. That's where we start the lecture. A function f is called a one-to-one function if it never takes on the same value twice. That is, two different inputs have to give you two different outputs. Okay, that's what this says. F of x1 is not equal to f of x2 whenever x1 is not x2. Different inputs must end with different outputs. To check whether a function is one-to-one, or shorthand for one-to-one, there are several ways you can check it. I'm listing some popular and easier one depending on what kind of function you are having, and I'm going to show you how they work on my example. So here's my example. Function f of x equals square root of x, and we're going to check whether it is one-to-one. So the first way, horizontal line test. To test whether a graph is a function, we use vertical line test. To test whether the graph represents a one-to-one function, we use horizontal line test. Of course, here we are talking about x as independent variable and y as dependent variable. So square root of x is half parabola. And when you use horizontal line test, pretty much you just push through all the horizontal lines and see if anywhere a horizontal line will meet the graph more than once. If you have a horizontal line that intersects the graph more than once, it fails. Ours doesn't. The horizontal line either not touching our graph or only meet it once. So it passes the horizontal line test. And if it passed the horizontal line test, it is a one-to-one function. That's my first way. Second way, you really just set up two different axes, x1 and x2, and say their outputs are the same. So my f of x1 equals f of x2. But what does it mean? It means square root of x1 is square root of x2. That's what function f is. Then I square both hand sides. I get x1 equals x2. So what it says is same output must come from the same input. Same y coordinate have to come from the same x coordinate. Then the third way, let me put it here. In equation y equals f of x, you solve for x. If there is only one solution for each of the y in the range, it is one-to-one. So in the equation y equals f of x, which is square root of x, y equals square root of x, you solve for x. Square root, again, square both hand sides. You get y squared equals x. Or remember, you solve for x, x is y squared. For each y, you have one solution. You don't have x equals square root of, I don't know, y squared plus 4 or something like that. You don't have the plus or minus. So you have only one solution, which means the function is one-to-one. The last way, you use derivative. If the derivative of f is positive everywhere on its domain, then the function f is continuous and increasing everywhere. If that's the case, it can't go back to the same number. Similarly, if the function is decreasing everywhere, of course here we are assuming function f is continuous, okay? If the derivative of f is negative, then the function f is decreasing constantly, like then there's no way it go back to the same y. So you just need to compute the derivative. F of x is square root of x, which is x to 1/2. So f prime of x is 1/2 x negative 1/2. Let's rewrite it as 1/2 times square root of x. So 2 square root of x on denominator. Square root of x is greater than 0, then putting it on denominator, multiply by 2, none of them will change the sign. This is positive on its domain, which is from 0 to infinity. 0 is not included because derivative is not defined, but that's an isolated point. We can ignore that. So actually f is increasing and 1 to 1. If we already know f is 1 to 1 with all the ways that we verified, say f has the domain A and the range B, then what is its inverse function? Our f maps x to y. Maybe x1 to y1, x2 to y2, but different x's give you different y's. The inverse function is the backward. Let me do this. So when you go this way, that's f because I already used the color. And when you go backward, that's f inverse. So from y1 to x1, from y2 to x2, that function is f inverse. F inverse of y goes back to x. Okay, and also please observe that the domain of f, which is the left hand side, these are the domain of f, which will be the range of range of f inverse. Similarly, the range of f, which are the y's, will be the domain of f inverse. Now, how can we find this f inverse function? So pretty much what we need is we need to know which x give us the y. So we want a formula for x in terms of y. And this is how we are going to do it. Again, I'm going to demonstrate this with my example. First, we write y equals f of x. So my function here is f of x equals 2x plus 1 over 3x minus 4. First, I replace my f of x by y. I need a function of only x and y, no f, so I can solve in terms of y. Then I solve for x. Clear the denominator. Then I distribute. Remember, I'm solving for x, so all the term with x goes to the left, terms without x goes to the right. Then I pull out the coefficient and divide by it. This gives me x equals 4y plus 1 over 3y minus 2. Now, this is a very important step. Up to here, we rewrite f of x as y, and then we solve the x in terms of y. Next, to express f inverse as a function of x, we are going to interchange x and y, which means x becomes y. This is the interchange step, okay? And y becomes x. And finally, we use the interval notation. 4x plus 1, 3x minus 2. So we replace the function notation by y. Solve for x. Interchange x and y, and put f inverse of x back for y. Another example. Same thing. First, f of x becomes y. Then we solve for x. This is easy to solve. X equals 1/2 y. Then we interchange x and y equals 1/2 x. Finally, I use inverse function notation. F inverse x is 1/2 x. So if function f is doubling the input, the inverse will be half the input. Yeah. So I did this example because I want to show you the picture. On the coordinate plane, this is my x, this is my y. So let me do some basic tracing so I know where they are. Y equals 2x is here. And f inverse of x equals, that's the inverse, 1/2 x is here. And what I want to show you is that these two lines are actually symmetric with respect to y equals x. Okay, as I put in the remark, the graph of f inverse is obtained by reflecting the graph of f about y equals x. So you can imagine you can take the whole coordinate plane up and flip it so that your y-axis goes to x-axis, x-axis goes to y-axis. You know, that's how you flip it. Meanwhile, the f function goes to f inverse function. Now you can try practice number 1 and number 2. Here's the main theorem of today's lecture. If f is a one-to-one continuous function defined on an interval, then its inverse function is also continuous. So, well, it has to be one-to-one to have an inverse. Continuous function give you continuous inverse. Okay, so pretty much the graph is one piece, then you flip it, it's still one piece. That's what it is. Now the second part, if f is a one-to-one differentiable function with inverse function f inverse, then and the derivative of f inverse of a is not 0, then we can compute the derivative of f inverse at a. This looks a little bit complicated, so let me tell you what's really happening here. Say your function f maps b to a. This is your f. Then f inverse of a will equal to b. What it says is if at b the derivative is not 0, then you can, if you want to compute the derivative of an inverse function, you can go back to where it came from with the original function, but at the end you flip it. Okay, this f prime is f prime of b. So f prime of b and f inverse of a, f prime of b and f inverse prime of a, the derivative of f at b and the inverse derivative at a, they are reciprocal. Why is that true? Because when you flip it, x becomes y, y becomes x. And derivative is changing y over changing x. When you interchange the variable, it becomes, changing x over changing y in the old version. That's why the derivative is flipped, and that gives you the reciprocal of the counter side. Now let's use an example to see how it works. Show that f of x equals 2x third plus 6x plus 3 is 1 to 1. And find the f inverse derivative of 3 without finding the formula for f of f inverse. So what I'm saying here is I don't want you to solve for f inverse. But meanwhile, I want you to find this derivative. How are you going to do it? First, you need to show it's 1 to 1. We are going to use the derivative because, in order to apply the theorem, you need a derivative anyway. So f prime of x equals 2 times 3x squared plus 6. 6x plus 6. Sorry, 6x squared plus 6. X squared is greater than 0. So 6x squared is also greater than 0, plus in 6. Actually, it's greater than or equal to 6, but doesn't matter. I just need it to be greater 0. And that means f is 1 to 1. Which means it has an inverse function. Now we want to find f inverse, the derivative of f inverse at 3. So here's my f. It maps something to 3. And the f inverse will map this 3 to that missing number. And we want to find the derivative of f inverse at 3. How are we going to do it? We are going to do it in the counter side. The number that gave you 3 under f. Then we use the derivative of f. Flip it. Okay, now the question is, which number maps to 3? So f of x equals 3. 2x third plus 6x plus 3 is the right what x will become, and actually that's 3. That means 2x third plus 6x equals 0, and we factor out 2x, we have x squared equals 3 equals, sorry, x squared plus 3 equals 0. 2x equals 0, that's x equals 0, x squared plus 3 equals 0, x squared equals negative 3, you have no solution. It has to be no solution, remember? You are having a one-to-one function, which means there can only be one x value giving you 3 for the y coordinate. So you can't have 3 answers. You can't have 3 solutions, okay, or 2. You can only have one solution, which is 0. Then my f inverse taking derivative at 3, again, this side becomes the reciprocal of this side, equals 1 over f derivative at 0. I already know what the derivative of f is. I computed it in the very beginning. So it's 1 over 6 times 0 squared plus 6. Well, 1 over 6. That's a 6. Okay, so here, first, I'm showing the function is 1 to 1 so that it has an inverse. To show a function is 1 to 1, especially seeing that you are going to find the derivative of the inverse function, hopefully the derivative is positive everywhere or negative everywhere. Find its derivative and see if it's positive or negative, but you need to show it. After that, you are going to find the pre-image, which is, pretty much the x coordinate, the x value that gives you y value as whatever given number, here 3. So solve this equation. Which input give me an output 3? I set up my equation and I solve for it. You should only have one solution because it's 1-to-1. Finally, use the theorem. The derivative of an inverse function equals the reciprocal of the derivative of the original function at the corresponding point. Then you can just use the function f, because you have the formula, with the counterpart, which is the preimage of the number. And don't forget to take the reciprocal, flip it. Okay, now you can try practice number 3 and number 4. In the last part, I want to say a little bit about natural logarithmic function. First of all, we're going to redefine this whole thing using calculus. Definition. We are defining them this way, so we are calling them logs, okay? The natural logarithmic function is the function defined by ln x, is the integral from 1 to x, 1 over t dt. And here x has to be greater than 0. This integral is the area between 1 and x under function 1 over t, or 1 over x, right? So when your x is greater than 1, this is the graph. You are really just having the area between 1 and x under 1 over t. But when x is less than 0, I meant 1. When x is less than 1 but greater than 0, why greater than 0? Because you need to make sure 1 over x has 2 branches. You need to remain on the same branch that we're picking, the one in the first quadrant. So you can't really go less than 0, go less than 0. You go back to this branch. When x is less than 1 but still greater than 0, the integral from 1 to x become negative, in the sense the lower limit, 1, actually is higher, but the higher limit, x, is lower. So in this case, the integral of 1 to x, 1 over t dt, will be negative x to 1, 1 over t dt. And that is the area that we're looking at. So this is the ln x. The ln x actually is a negative of the area of the blue part that you see. Now, the derivative of ln x, and here I'm recalling that this is the fundamental theorem of calculus. Okay, so when you have, pretty much it says integral and derivative are inverse of each other, inverse operation of each other. So when you are having an integral from a constant to x, then whatever the integrand is the same as the derivative of the integral. So you take an integral, then you take derivative, you go back to the function you start with. Anyway, based on this fundamental theorem of calculus, the derivative of ln x, write out what ln x really is, right? That's the definition. You are taking the derivative of the function with respect to x, and that is, you are just plugging in x in 1 over t, and you get 1 over x. So that's the reason we are defining the logarithmic. One of the big reasons, because we need something for x negative 1. In general, when you do integral xn, you say n plus 1, and then you take reciprocal. But you can't do that with negative 1, because when you do negative 1, it becomes negative 1 plus 1, and that's a 0. You can't do 1 over 0, so that has been a problem. Now, we have this function whose derivative is x to negative 1, or 1 over x. Well, based on this definition, actually, we still can maintain all the laws of logarithms that we know. Log of a product is the sum of the logs. Log of a quotient is the difference of the logs, and log of a power, you can pull the exponent to the front as a coefficient. So these are all true because of our definition of Ln function. Okay, let me box it nicely. I'm not going to show all of them, but let me at least show the first one. So Ln of xy, by definition, is the integral from 1 to xy 1 over t dt. Now I'm going to take derivative with respect to x. So d dx ln xy will be d dx, this integral. Again, fundamental theorem of calculus, I'm really just having the xy plugged in here, but that's not x itself, there's a chain rule. So it will be 1 over xy times xy, well, I don't want to say prime d dx xy. So actually this is 1 over xy times y. Maybe this will make it better. Y actually is the coefficient and x is the independent variable. So it equals 1 over x, which means the derivative of xy is also 1 over x. If that is the case, then ln xy will be antiderivative of 1 over x. But this, by definition, is ln x. Now I'm going to plug in x equals 1. You will have ln of 1 times y equals ln of x, ln of 1 plus c. But what is ln1? ln1 is the integral from 1 to 1 over t dt plus c. Well, any integral from on the same number is 0. So this equals 0. This is 0 area. So that gives us ln y actually equals c. Bring it back here. You have ln xy equals ln x plus ln y. Well, I did all this to just show you we have the log, the rules of log that we have known since maybe 2 courses ago are still true. Not because we knew they are true, but based on the new definition, they still hold. I'm not going to show the other two, but that's the idea. If you don't understand it, perfectly fine. Just ignore this part. But you need to know when we define something in calculus or in math in general, we try to keep the old laws still correct when we extend, a definition to more choices of number. Okay, finally, I hope you still can see it. Let me circle it. E is the number such that ln e equals 1. So E is that magic base of log, natural log. But here, based on this integral definition, what you have is you need to make this area equals 1. When this area equals 1, you keep following the 1 over t function, and somewhere the area will reach exactly 1. That number give you an area 1 is E. It turned out to be the 2.71828 number, but doesn't matter. It's a number that is greater than 1. That's all it matters. The last part, we are going to go over some basic laws of log, how we are using them, and the one we just used. Log of a product is the sum of the logs. Log of a quotient is the difference of logs. And then the log of a power becomes a product. With these laws, we can expand log of a product and the quotient and the power into a bunch of log terms with addition and subtraction. So the first one, I'm trying to expand each log expression as much as possible. Ln of x plus 2 square root. Square root means 1/2 power. Then I can give it to each of the factors in my base. Ln x 1/2, x plus 2 1/2. Then the product becomes a sum of 2 logs. And then I pull my coefficient to the front. 1/2 ln x plus 1/2 ln x plus 2. Next example, same thing, we expand it. So ln of this equals, I don't think you should write this step, but I want to show you why it is true in general. So pretty much a quotient or fraction is the numerator divided by denominator. So all the factors on top is positive in their ln's, but all the factors, this is x plus 1 squared, on the denominator are negative. Okay, so I think you're okay with square root of x is x 1/2. I'll just pull it. So ln 27, I don't want to write it at 3 to the 3rd power, but if you want to, that's fine. Square root of x becomes x 1/2, so I pull the coefficient to the front, and also the 2 as exponent becomes coefficient in front of ln, and finally x plus 4. Ln of x plus 4. Notice that we don't have laws for log of a sum or log of a difference. So when you have log of a sum or difference, the sum and difference remains in parentheses, and you can't expand those logs. For example, this. Okay. All right, that's it. Now you can finish the practice.